Okay. No, I think I'm ready to start. Okay. So last time we ended with that virial equation, which is a polynomial in P. Just making sure I'm recording. Yeah. Okay. That shows the compression factor as a function of pressure, and it's a polynomial. And it's really not very satisfying because there's really no intuition about that equation. You can't tell how things depend on other things, pressure, volume, temperature, volume, things like that. So what I'm going to do today, or at least the start of today, is to tell you about a more satisfying equation for a real gas that is called the van der Waals equation, the same van der Waals that made up those van der Waals forces that are also known as dispersion forces. Anyway, and so what the van der Waals equation does is it sort of attacks the two major weaknesses with the ideal gas law that become evident as the pressure increases. So this is at high pressure. So the kinetic theory, if you remember, assumes that gas molecules have negligible volume, but actually gas molecules do take up space. I mean, the molecules themselves, not talking about them expanding to fill the container volume, but they do have their own volume, so they do take up space. And so what happens is that they really cannot, two of them cannot occupy the same volume. And so I'll show you what that leads to. It leads to something we call excluded volume. And that the gas molecules actually do interact, and they definitely attract one another. And that has to be taken into account. You know, in the kinetic theory, we assume that all the collisions between gas molecules are completely elastic, no energy changes in anything. And that's just not the case when you have intermolecular forces. So it's possible to, like I said, adjust the ideal gas law to account for these facts. And this is what the van der Waals equation does. So I'm going to show you the first, we're going to take up the taking up space issue, okay? So if we have a container with the volume shown, and I've showed the gas molecules as these really tiny dots. And so this is illustrating that they have, quote, no volume, which of course you can't illustrate that. So it has a tiny dot. But what happens if now we make the dots not so tiny? And so we can represent a gas molecule as having an actual volume. So what you can do is sort of picture in your head that the fact that the molecules have some volume means that gas molecules in that container do not have as much free space to move around. So if you crowded all those molecules into the corner here, you would see that this volume, this red volume here, is excluded. It is not included in the free space volume for molecules to move around in. So we call this excluded volume. And what we want to do, and the reason why there is this excluded volume, so why is this excluded volume? And it's because gas molecules cannot be on top of each other. And why can't they be? Because if they were, there would be repulsions. If they were very close together, you'd even have nuclear repulsions, which would be very repulsive indeed. So anyway, this free space volume, the volume the molecules have to move around in, is actually smaller because of the volume that the molecules take up themselves. So if we have 1 mole of gas in this container, and we say that the and if B submolecule is the volume of just one molecule, And then you multiply that by Avogadro's number. So we have Avogadro's number times the volume of one molecule. This gives you the volume of 1 mole of molecules, the molecules themselves, and we call that B. So that's going to be one of our van der Waals parameters, B. For a 1 mole sample, this B is the excluded volume. If you have n moles, you'd have to multiply that by n. And so you'd have NB being the excluded volume, right? That's what this is here. So if we start with the ideal gas law for 1 mole, and let's just create the ideal gas law for 1 mole by dividing by the number of moles here. So here your moles goes away. So this becomes, this V over N is the molar volume. So this is kind of an ideal gas law for 1 mole. And it uses the molar volume instead of the volume, and it doesn't have an N. And so we end up with this formula here. We haven't done anything with the van der Waals, with these repulsions yet, with this excluded volume. So what we need to do now is, we know that this is not really the free space volume. We have to adjust it by subtracting out the volume of 1 mole of molecules. So we end up with P Vm minus B equals RT. And that means that P would be RT over Vm minus B instead of RT over V molar, right? Which is, that would be the original ideal gas law per mole. So we have adjusted for the excluded volume. Okay, if we did it with the regular ideal gas law, we would have to change the volume. We'd have to subtract N times B. And so we would end up with P equals nRT over V minus NB. So there's just these two versions. Okay, so that's, now we've taken into account the excluded volume. So that's the first correction. That the van der Waals equation makes to the ideal gas law. Okay, so now for the second correction, and that is that gas molecules do interact. So I drew a picture like this earlier, like I think in the last class. Did I? Yeah, to illustrate what happens at moderate pressures. And so this molecule here is about to strike the wall, but it is pulled away by attractions to its neighbors. Okay, and so that is what decreases the pressure to be lower than what the ideal gas law would predict. So attractions between gas molecules pull them towards each other and away from the container walls. All right, and that reduces the pressure of the gas. So the question is, what does this pressure reduction depend on? Well, actually, first, what does the pressure depend on? Let's just look at that. And I talked about this when we did the kinetic theory, and the pressure depends on the frequency of collisions and the force of collisions. So you have the number of collisions here related to the frequency and the force per collision. So this is, we talked about how the product of these two would be the total force of all the collisions. And we'd have to divide that by the area. So what happens when these molecules are prevented or slowed down and they don't hit the wall with the same force, what happens is that both things decrease. Both the number of collisions decreases. So at a certain time, the frequency of collisions would decrease due to attractions. And you would also have the force per collision decreases as well, because of these attractions. Okay. All right. So what we want to do is come up with some sort of expression on what that pressure reduction, what that force reduction or what the pressure reduction would be proportional to. And if you think about it, what's important here is to consider, how many molecules. So we call that number density of molecules. And the reason it's important to think about this is if you go back to this picture, if you have more molecules in the container, there's going to be a greater attraction to those molecules about to hit the wall, and that will reduce the pressure. And of course, it will reduce the number of collisions. So the fact that if you have more molecules there, so more molecules or greater density, right? Greater number density. The force per collision and the number of collisions will both be lower. So I guess I would say that the reduction of each, so this is kind of the reduction of each factor, since each depends on the number density, the reduction of each factor is going to depend on the number density. So, and the number density is just the mole, would be like the moles over the volume. So, and I'm trying to make a very simple argument here that each of these factors depends on the number density, and the reduction in the pressure would also, the reduction of each of these factors would depend on the number density. So what I'm going to say in conclusion is that the reduction in the pressure is going to be proportional to the square of the number density. And this is exactly what we do. We say that the reduction in pressure is proportional to n over v squared, which means it's equal to a constant. We call that constant A times n over v squared. So when we go to reduce the pressure, we had the first correction here. Now what we're going to do is we're going to subtract this A n over v squared, because we believe that the reduction in pressure should be proportional to the number density for each one of these factors. And that's why we pick up two of those factors. So the van der Waals equation is this. Okay, this is the basic van der Waals equation. If we did it in the per mole version, let's see, we had P equals RT over the molar volume minus B. So now we'd subtract A n over V squared, but n over V, right, is 1 over V over n, which is 1 over the molar volume. So this becomes RT over Vm minus B minus A over Vm squared. Okay, so that's another version of the van der Waals equation. Okay. And that's what this is called. So these two van der Waals parameters, A and B. B is the volume of 1 mole of actual molecules, which could be gotten from bond lengths and making assumptions about the size, about the shape of a molecule. The A parameter depends on the degree of attractions. Now, both of these can be found experimentally, although it's pretty complicated how that's done. So I won't really be able to tell you how that's done this semester. I'm going to sort of skip that topic, but it's related to so you can actually, these are related to what I'm going to call critical parameters. but I'm not going to be able to tell you more about that. Well, we'll do critical temperature, but I'm not going to tell you how they're related. But I do want to take a look at some of the values of these things, because these values tell you a story, or just, sort of corroborate some things you already know. So if we think about comparing, say, hydrogen and chlorine, okay, so here are the numbers for H2 and Cl2, A and B. We have 0.0247, 0.6579, 0.0266, 0.0562. So the first thing you can notice is that Cl2 has a greater B value. Well, that makes sense, right? Because Cl2 is larger. So that checks out with our view of things. Cl2 also has a greater A value. Why is that? Well, both of them are nonpolar. But if you remember, a nonpolar molecules can interact by what sort of forces? Right? Those are the dispersion forces. And dispersion forces increase as electron cloud size increases. And you certainly have a larger size of electron cloud in Cl2 than you do in H2. So that makes sense if you have a greater A value for chlorine. Okay, let's take a look at N2 and CO. So N2 versus CO. I think this was H2 and CO. Okay, N2 versus CO. So first I want to say that the B values, so let's see, we have N2 and CO, A and B. There's the values. So the B values are very close. So how do we understand that? Well, N2 and CO have the same molar mass. They both have 10 valence electrons. So you expect a very similar size. Okay, so that goes along with what we think. Now let's talk about the A values. So let's see. We have an A, the A for CO2 is a little greater. Is that something that we would expect? Well, CO has a dipole. Right? N2 only has dispersion forces. So yeah, you would expect COs to be greater. In fact, you might expect it to be even a little greater than that because it has a dipole. But so what you can sort of conclude from all this is that dispersion forces are pretty important. Because if they weren't important, then CO would really have a much greater A value than N2. So it's interesting to look at these numbers and compare them to sort of your general chem kind of knowledge about these molecules. Okay, so I put another sentence here about how dispersion forces must be pretty important, or else CO's A value would be much greater than N2's because carbon monoxide has a dipole. Okay, so now I'd like to compare water, NH3, and CH4. So let me get those numbers down. So those A and B values are you could see that water has the greatest of the three, which is no surprise. I haven't put any units of these numbers down because the A and B values have very strange units. And, if you look at the van der Waals equation, you see each of these things has to have, each of these terms would have units of pressure. So you can imagine to get a unit of pressure when dividing by liters squared, it would be weird. Here actually B is very easy. It's just a unit of volume. So that I was wrong about. I shouldn't have said they were difficult. But anyway, so what we see here is if we compare the A values first, we see that, of course, water has the greatest A value. And that's because, of course, it has the greatest intermolecular forces, greatest magnitude of intermolecular forces. And why is that? Well, of course, first of all, CH4 is nonpolar, so it doesn't have anything but dispersion forces. And water has hydrogen bonding, which so does ammonia, but water's hydrogen bonding forces must be stronger than ammonia's. And the reason for that, well, oxygen has a greater electronegativity. So water has greater magnitude dipole. And also, I think another thing is that you have a more even distribution of delta plus and delta minus. So in ammonia, you have 3 delta plus sites. You're not going to be able to find a lot of delta negative ammonias, right? There's 3 times as many delta positives as delta negatives. So you have a more even plus minus distribution here in water. So you could see that water's A value is higher than that of ammonia. And of course, they're both higher than that of CH4 because of the strength of hydrogen bonding forces. Now, as far as the size, the B factor is a B value, you could see that the size increases as you go from water to methane, according to this. In fact, if we go down here, I'll write down that the OH bond length is 0.948 angstroms, whereas the CH bond length is 1.091. That's probably largely due to the size of the carbon being a little bit larger than oxygen. Remember, size decreases across the periodic table for atoms. And also, of course, CH4 has more atoms, right? And you have electron clouds around each one of these atoms. So, anyway, that's probably why the size is the way it is. Anyway, that's really all I have to say about that. Okay. All right, so now what I'd like to do is shift gears a little bit and actually talk about another approach to understanding real gases. And that is through their PV isotherms. Okay, so we're going to look at PV isotherms. Of a real gas. And the gas that we're looking at here is methane. All right. And so let's talk about these. If this was an ideal gas, so what would it look like if it wasn't for an ideal gas? So for an ideal gas, if you remember, they just look like this. It's just completely P is proportional to 1 over V. And we're not seeing that in this drawing here, in this diagram of the PV isotherms for methane. So let's take a look at this. First of all, I want to comment that at high temperatures, there is ideal behavior. Okay, so you would expect that as you decrease the volume, you would increase the pressure inversely proportionally. So over here, we have ideal behavior. But now I'd like to take a look at this 165 Kelvin. Okay, so this is a lower temperature. And I want to look closely at what happens as you decrease the volume. Okay, and we're going to hold the temperature constant at 165. Okay, so as you go from A to B, for example, I know you have it looks like it's ideal. It looks like, you have this sort of inverse proportionality here. As you decrease the volume, you're increasing the pressure. It looks like it might be ideal. But its looks can be deceiving, okay? Actually, what's happening here is these are pretty small molar volumes. But so it's really not ideal. That the pressure is not as high as the ideal gas law would predict. Let me just make a sort of exaggerated illustration of that. So if this is what your ideal isotherm would look like, what we're seeing here is more like this. It's not, the pressure is not increasing as much as volume decreases, okay, as it should, according to the ideal gas law. And why is that? Well, that's because you have some attractions going on here. These, like I said, are relatively small molar volumes, and I'm going to actually calculate that a little bit later. I'm going to do an example a little bit later. But anyway, so don't think, it's not quite ideal there. But now let's see what happens. This is what I really want to look at for now, is what happens at point C, okay? And if you look at the diagram closely, you see what happens at point C, as you continue to decrease the pressure at point C, sorry, decrease the volume, the pressure stays constant. And that is certainly not the behavior of a gas. This is actually because liquid has started to form. And the first drops of liquid are at point C. Okay, so what's going to happen to the pressure as you decrease the volume of this now gas liquid mixture? So here I have a diagram. This would be point C. Now, these smaller dots represent gas molecules. I'm going to put this in red so you can see it. And these are liquid droplets. So this is the beginning of liquid forming. So when you get to point C, you start to see some liquid drops. So now what happens as the volume continues to decrease? As the volume continues to decrease, what you're seeing is now the liquid is pooling at the bottom, okay? But and you could see that, this has a somewhat of a smaller volume than this does, that you've compressed it a little bit. I mean, this whole thing doesn't look like much, but now you can definitely see the volume is smaller. And so as you decrease this volume, what you're doing is you're forming more and more liquid. You're taking molecules out of the gas phase and putting it in the liquid phase. And the pressure is the pressure exerted by these gas molecules on the walls of the container. And that pressure stays the same because you have a smaller number of molecules, but it's in a smaller space. And what happens is, as the volume continues to decrease, the pressure of the gas does not change. Okay, so let me show you the next slide, which is the one I gave you guys, that the pressure in the chamber in this picture, right, caused by these gas molecules, and here, these pressures are the same. And we have a name for that pressure. Okay, we call it the vapor pressure of the gas. It's the pressure of a gas in equilibrium with its liquid. So P vape, the vapor pressure, is the pressure of a gas in equilibrium with its liquid. So we could say the pressure above the liquid, or something like that. And that pressure stays the same. So if you go and you look at this diagram again, you see this is completely horizontal here. And that this is actually the vapor pressure. This is the vapor pressure at 165 Kelvin for methane. These are very cold temperatures. I mean, methane is, it's a gas at fairly low temperature. So 165 Kelvin is, 273 minus. So you add 273 to that. It's like, let's add 365 to 4. It's like 450 degrees C. No, wait. Oh, no, sorry, I did that wrong. It's minus 108 degrees C. So all this action is happening at a pretty cold temperature for methane. All right, so let's see. So what happens now at this point, which is labeled E, right? So that's at the end of this horizontal region, right here, point E. At point E, all the gas has been converted to liquid. So that's what this is here. This is point E. I think it says that on there. Okay. And now what happens if you continue to decrease the pressure? It skyrockets. Okay. But let me go back and talk a little bit more about what's going about the horizontal one. Okay, so we got the vapor pressure. It's the pressure of the gas equilibrium with its liquid. Oh, yeah. Here's another thing I'd like to say is that the pressure is the same. The vapor pressure is the same whether you have like 3 drops of liquid, like is shown in the first diagram, or whether you have, a lot of liquid sitting on the bottom of the container. Okay. All right, so if we look at this thing here, so this guy here, this is 165. The vapor pressure, I already told you this, is 30 bar at 165 Kelvin. And here, the vapor pressure is 40 bar at a higher temperature. That's 180 Kelvin. Okay. So you could see that vapor pressure depends on temperature. Which is something that, you learn in Chem 104. Okay, so that's another conclusion from this. And so let me just, one more thing I wanted to say. So what this is saying here with these vapor pressure values is at 180 Kelvin, you need there needs to be a pressure of 40 bar of vapor above the liquid in order to liquefy the gas. So you have to apply a greater and greater pressure to keep methane in the liquid phase as temperature goes up. So as temperature goes up, you need a greater and greater pressure to liquefy methane, or any gas. Let's just say a gas. And why is that? As the temperature goes up, why do you need more and more of a vapor pressure, more and more pressure above a gas for that gas to become liquid? And that's because as temperature goes up, you're giving more kinetic energy to the molecules. So the molecules have a greater kinetic energy. And so they can escape to the vapor phase. They have the energy to escape to the vapor phase more easily. So you'd have to keep applying a greater and greater pressure above that to get those molecules to go back into the liquid. So that's the thing, you know, that's what's going on here. You know, you have to have a higher vapor pressure at a higher temp. There's a higher vapor pressure at a higher temperature. You could think of that as the pressure that you need to liquefy, right? And so, you know, if molecules have greater kinetic energy, it becomes harder to put them into the liquid. So you need that greater vapor pressure. Okay. So there's one other thing I wanted to show you. I kind of did this a little backwards, but there's one other thing I wanted to show, which I'm going to go back to this diagram. So this is the 165 Kelvin. Because I wanted to use this diagram to calculate kind of a sort of a crude compression factor. And first, what I'm going to do is talk about the ideal situation. So let's suppose that we had 165 Kelvin, but way, way out here. Okay. In other words, let's pick a pressure of 1 bar. 1 bar would be way out here somewhere. Okay. Now at 1 bar pressure, the methane is going to behave ideally at 165 Kelvin. Okay, it's going to be way out there. It's a very low pressure. So let's call that 0.1. Okay, so we're going to do a calculation. And what we're going to do, you know, is it'd be way, way out, right? This is 0.5. So you can imagine it's going to be like across the room, maybe down the hall. Okay, so let's calculate the volume. And let's do it for 1 mole. At 1 bar, so pressure is 1 bar. I'm going to do this. This is in bar, so I'm going to do 0.08314 liter bar per mole Kelvin times 165 Kelvin over 1 bar. And this is 13.7 liters. So that's why I'm telling you it's way down the hall. Okay. I'm using the ideal gas law because the gas is behaving ideally at 1 bar. Okay. So now let's take a look at point A to point B. We're going to look right over here. Okay. So that's the second, is from going from A to B on the diagram. Get some more space because I kind of did this in the wrong order, but that's all right. Okay, so as you go from A to B, let's look at this diagram. At A, it's approximately maybe 0.45 liters from the diagram, very crude. The temperature is 165 Kelvin. And the pressure, this is the actual pressure, of course, that's what's on the diagram, is, let's see, let's say it's 20 bar. Okay, so now let's use this information. We're going to calculate a Z value. Okay, so we know that Z is P over P ideal. We already have P. So what would P ideal be? It would be RT over V. So it's going to be 0.08314 times 165 divided by 0.45, right? Take your calculator out because these numbers are slightly different, of course, than the ones I prepared, but it's not hard to do. 0.08314 times 165 divided by 0.45. And it's 30.5 bar. So now if we formulate our Z value as P divided by P ideal, so that's 20 bar over 30.5 bar, okay, you could see that that number is well under 1. It's 0.66. So Z is less than 1. And so this is where attractions are dominating. Okay. And so what I said before about how the pressure is not rising as volume goes down as if it were an ideal gas, it's basically rising less. The pressures are lower. And indeed, you see that you have these values of Z that are less than 1, which imply that attractions are dominating this picture here. Okay. So for 165, the liquid starts to form here at point C, as I said, and you have to have a 30 bar pressure. Vapor pressure here is 30 bar. That's what this question mark is. It's really given before any liquid will form. You know, that's a really high pressure. Now you'll notice the molar volume here is like between 0.2 and 0.3 liters, really, really small molar volume at this point. Okay. So so this, like I said, this vapor pressure depends on T. As it goes up, you need a greater and greater pressure to liquefy a gas. And that's because what you're combating is the molecules that are, you know, higher temperature, they're trying to get into the gas phase. So you need a greater and greater pressure to keep them in the liquid phase at a higher temperature. And there's that equilibrium point there where those two things sort of balance out. And so just to point out, we call this region in here inside this crazy curve, we call that the liquid gas region, because for all of these horizontal lines, we have an equilibrium between liquid and gas, and we have a vapor pressure at each of these temperatures. So we have P vape at whatever, let's call this 150. We have the vapor pressure at 160, you know, et cetera. Okay. Now, here's the interesting thing, you see. Just see what I have here. Okay. So if I take and just sort of look at this curve, what happens here? What happens at 190 is here you are, you're decreasing the pressure. Okay. But there's no liquid gas region there. So what happens at this temperature is as you keep decreasing the volume, no liquid forms. And that's regardless of the pressure. Here you are decreasing the volume and the pressure's going, let's put it in yellow. Oh, well, I'm getting all screwed up here. Okay. You never have a liquid gas region. There is no liquid that forms. And that is called the critical temperature. So for methane, 190.6 Kelvin is what we call the critical temperature. And the critical temperature is the temperature above which it is impossible to liquefy a gas. Regardless of what pressure is applied. Okay, so, typically, you'll have for most gases, for most substances, I should say, some kind of liquid gas region, where you have, your curve going up, and then you have a solid line, and then you have the pressure going way up because of it all being liquid. And then at some point, you have this crazy thing where you have this critical temperature. Okay. Now, every substance has its own critical temperature. And this point here, every substance has its own critical point. This is called a critical point. It has a TC, right? That would be whatever this temperature is here. It would have a critical volume and also a critical pressure. So every substance has its own critical point. Now, what's it like there, right? What's it like at or above the critical point? So at this point and above this point in terms of temperature, what you have is something we call a supercritical fluid. Okay, so where this happens is over here in this part of the curve. The shaded region is what we call a supercritical fluid. Okay, and what characterizes it is it fills the container. So in that sense, it's like a gas, but its density is too high for it to be a typical gas. So it's sort of got a liquid-like density. But you will never see, there are no droplets. There's one phase. In other words, you don't have gas and liquid where you see a line in between them. It's just one phase completely. And this happens when the pressure is greater than the critical pressure and the temperature is greater than the critical temperature. So it's above this isotherm here that's representing the critical temperature. And actually, I probably shouldn't draw this above here. There, let's put it there. There we go. Okay. So I'm going to do a close-up of the critical, of this diagram for carbon dioxide. All right, so this is for CO2. And this is what we call supercritical CO2. See, it's at pressures above the critical pressure. This is the critical pressure, and temperature is above the critical temperature. So this is the critical temperature. That's the isotherm that goes up to that point there. All right. And you may ask, well, how would you make this? This actually has a lot of, so supercritical CO2 has a lot of industrial uses. So you ask, how would you make it? you know. So what you would do is you would start at a temperature, start at a temperature that's above the critical temperature. Well, for CO2, that's not hard to do because the critical temperature for CO2, it says it here, it's 304 Kelvin, but that's 31 degrees C. So that's like, room temperature practically. So you would start here at maybe, this is the critical one. So like this one is 310, okay, 310. So you might start here. Okay, and then what you could do is you could just increase the pressure. So you could increase the pressure until you're above the critical pressure. So we'd start here. Increase the pressure to be above the critical pressure, and that's it. You have supercritical CO2. The other thing you could do, alternate, you would start at 310 and go along an isotherm. So you would decrease the volume at constant temperature and go along an isotherm. So you would be over here and then you go this way. And then you'd get into the region where so you have supercritical. So this would be the alternate method. Go from 1 to 3. Okay. You might ask, well, what's a use of this? And those of us who don't always drink caffeinated coffee anymore, that's a main use. Most commonly known is the extraction of caffeine from coffee. So how did this used to be done? Okay, well, there's different methods. I know there's even more methods now because I see on coffee that I buy that's decaf, it says water method. I don't even really know what that means. But in the past, they used toxic substances, really, like a solvent, methylene chloride, for example. I don't know. I don't really want to have use coffee beans that methylene chloride's been anywhere near. Okay, but they would use, they would extract with methylene chloride, extract out the caffeine, and then they would have to dispose of the CH2Cl2. I suppose they could reuse it, but eventually they'd probably have to dispose some of it. There would be a toxic residue left on the coffee. And also it led to kind of a bad taste. So now there's a much greener method where you start with here's your green coffee beans over here. Okay. And what you would do, you start with the temperature greater than the critical temperature. And then you would make the pressure very high. Now, the reason okay, so you have to get into the supercritical CO2, but you would make the pressure high, even higher than what you need to have supercritical CO2, because as you increase the pressure of the CO2, the caffeine becomes more soluble, because caffeine is soluble in supercritical carbon dioxide at high densities, right? So the more you pressurize at the higher density, and so you pass high pressure supercritical CO2 through those coffee beans, and the caffeine is soluble, so it dissolves in the supercritical CO2, and after it passes through, you decrease the pressure. And so then the caffeine drops out of the supercritical CO2. You can isolate the caffeine and you can recycle the carbon dioxide. So it's a very nice, neat method of getting the caffeine out of coffee for people like us who older folks who don't want to like drink coffee all day long because they're not in school anymore. All right, so I wanted to show you this because I showed you the surface representing the states of an ideal gas. And I wanted to, show you how different it looks for a real gas. So we have these isotherms over here with these horizontal region representing the pressure, that's the vapor pressure. And here you have the supercritical fluid over there. So just a curious picture, right? It looks a lot different for real gases. Okay, so what I'd like to talk a little bit about next are critical temperatures and how these give an indication of how ideal a gas is, right? And the range of temperatures where a gas can behave ideally. Or I should say behaves, because they behave one way or the other. All right. So if a gas has a high critical temperature, what does that mean? Okay. If the temperature is high, the critical temperature is high, that means that a high temperature is needed for that gas to avoid liquefaction. Means that gas needs a high T to avoid becoming a liquid. Okay, so what that says is that that gas must have considerable or large attractive forces between its molecules. Must have strong intermolecular forces. In other words, attractions between molecules. Because to become a liquid, you need, you have those intermolecular forces that are pulling molecules together. And you would need a high, if you have those forces are strong, you need a higher temperature to get greater molar volumes to keep those molecules apart and stop from becoming a liquid. So increasing T increases molar volume and keeps molecules apart. If you have strong intermolecular forces, you'd have to have a higher temperature to keep them apart. So, so gases with high critical temperatures, they will not be ideal over as large a range, right? Because you'd have to be well above that critical temperature for the gas to behave ideally. So gases with high TCs have smaller range of temperatures where they behave ideally. And of course, the opposite, right? The lower the critical temperature, the greater the range of temperatures where a gas behaves ideally. And that would be a case when you didn't have a lot of intermolecular forces. So how about if I show you a chart of these molecules? Okay, we're going to fill in the last column later. But let's take a look at some critical data. And it's especially really, I just want to focus on the temperature for hydrogen, helium, et cetera, on this chart. And so I could ask the question, which of these gases would behave ideally over a wider temperature range? So in other words, which would be ideal at lower temperatures? It wouldn't need such a high temperature to behave ideally. So if you take a look at these two, these are the lowest ones, right? Hydrogen and helium, right? Hydrogen has a critical temperature of 33.2 Kelvin, and helium has a really hugely low critical temperature of 5.2 Kelvin. Wow. That means this gas will be ideal over a huge range, right? It cannot possibly at temperatures above 5.2 Kelvin, you can't liquefy it, regardless of the pressure. This will never be a liquid above 5.2 Kelvin. So it has a huge range where it can be ideal. Okay, so you have to be somewhat above the TC for it to be ideal. But, you know, maybe by 10 Kelvin, it would already be ideal. And then for all temperatures above that. Okay, so why? Why do these have such low critical temperatures? So these are so low because there are really very few intermolecular forces, you know, very small magnitude. Okay, and that's because, you know, there's no dipoles. They're very small. So they would have small dispersion forces. Okay. On the other hand, if you look at this chart, here's water. Okay. Water that has the highest critical temperature, and another high one is HCl. You know, and these are extremely polar. Okay, so water has the highest on this chart at 647 Kelvin. HCl has a pretty high one as well. And that's because these have very strong, I guess HCl is high too. So these gases, or these molecules, I guess I should say, have very strong intermolecular forces. You need a higher temperature to avoid liquefaction, because those intermolecular forces are pulling them together to become a liquid. Okay. All right, another really interesting point comes about if you calculate the compression factor at the critical point. All right, so if we take a look at this chart down here, what I've done, so how do you calculate this? So let's just do an example. Well, okay, it's not a big deal. Okay, we know that Z is P over P ideal. So it's P over nRT over V, right? That's P ideal. So it's PV over nRT, or PV over RT for 1 mole. Okay, so how do you calculate this Z? Is you simply, so Z at the critical point is just PCVC over RTC. And that's what happens if you take PCVC over R times TC. This is the value you get for hydrogen. Okay, so that would, I'm not going to do it, but it's 12.97 times 0.066 over 0.08314, because this is bar, liters, liter bar, mole Kelvin, and the TC would be 33.2. Whoops. Okay, that's that, and that comes out to 0.31. Okay, well, here's the interesting thing. What do you notice about these numbers? For all of these compounds, the Z value is approximately 0.3. Oh, well, as usual, water is considerably exceptional, okay, at 2.4. But we can always make an exception for water because of its tendency to, you know, it's got such strong intermolecular forces. So most of the Z's at the critical point are approximately 0.30. And I guess I want to ask the question, you know, why? Why would that be? Why would most gases have the same Z value at their critical point? Can we understand this? And yes, I think we absolutely can understand this. So let's pretend, if you're a gas and just a teeny bit above TC at PC and VC. So that would mean you're kind of like over here, right? This is PC, VC, and here's your TC. So let's suppose you're right over here, just above that, just above, right there. Okay, so what happens if the sample is cooled just a little bit? Well, you're in the liquid gas region. You get some constant condensation, you get some liquefaction. So that gas is just primed to be a liquid. It must have strong attractions there, right? Z is way less than 1. Strong attractions. Now, this is true whether the gas is helium or water. If it's just above its critical temperature, which for helium might be 5.3 Celsius with whatever its PC and VC is. For water, it's going to be 648. Did I say Celsius? I meant Kelvin. For water, it's 647, maybe 648 Kelvin, just above its critical temperature at PC and VC for water. And for both of those different substances at really very different temperatures, but both just above their critical points, if you just cool it down a little bit, you're going to get liquefaction for both. So what we would say is that all gases behave similarly at their own critical points. So at this point, gases are sort of equally non-ideal. Okay, and that's because they all have pretty much the same degree of attractions and repulsions. Yeah, so it makes sense. And this leads to something called the law of corresponding states, which we're going to skip this semester. But you should know this, that all gases behave similarly at their own critical points. And that's because their Z's are all about the same. They are experiencing the same degree of attractions. So which is, and they would all be liquid if you lower the temperature just a little. Or some liquid, all would form some liquid if T was dropped just a tiny bit. Okay, and that's really all I have to say about real gases. And so I'm done here. So bye-bye.